Now in this section we're going to talk about the integration rules, which are basically the antiderivative for the derivatives we talked about in the last section. So the first one is the logarithmic rule for integration. If we let u be a differentiable function of x, then the integral of 1 over x with respect to x is equal to the natural log of the absolute value of x plus c, and the integral of 1 over u with respect to u is equal to the natural log of the absolute value of u plus c. Now when you have this particular integral, you might find this a little bit easier to work with if you think of it as the integral of u prime over u dx, because remember du is u prime dx, so that might make your work a little bit better. So if we want to evaluate one like this, I'm going to first start by trying to make it fit one of my forms. The denominator here is an x, so if u equals x, then u prime would just need to be a 1. So I'm going to take this kind of extra 2 and stick it out front. So this would be 2 times the integral of 1 over x dx, which is going to be 2 times the natural log of the absolute value of x plus c. And we do have to put that that absolute value around that x, because you don't know from the integral whether or not x is positive or negative, and so in order to be able to plug it into the natural log, we have to force it to be the positive version of that. So you do want to put that in there. But in this case, I can actually use the power rule for logarithms and bring this in and write this as the natural log of the absolute value of x squared plus c. And the cool thing about when you square something is that it automatically becomes positive. So whenever you're raising your x to an even power like this, if you want to drop the absolute value bars, there's nothing wrong with that. You could just make it x squared because it will automatically be positive. If you don't feel comfortable doing that, if you leave them there, I'm not going to count off. But just know that as long as you're raising it to an even power, you can go ahead and drop those absolute value bars. Now this one's going to work similarly. I'm just going to bring the 3 out front. So this will be 3 times the integral of 1 over x dx, which is 3 times the natural log of the absolute value of x plus c. This is a perfectly valid answer. There's nothing wrong with this, but if you wanted to bring the 3 in as a power, you can. But in this case, because you're raising it to an odd power, you cannot remove those absolute value bars, because a negative number raised to an odd power is still negative. But either one of these answers would be perfectly fine. I'm not going to count off either way. And WebAssign should accept both as well. Now this is where things get a little bit interesting. In this case, I've got the integral of 1 over 3x minus 1 dx. So if I let u be equal to 3x minus 1, then u prime would have to be 3. And we don't have a 3. So I'm going to multiply by 3 over 3 on the outside, and I'm going to bring one of the 3's in. So this becomes 1/3 times the integral of 3 over 3x minus 1 dx, which is 1/3 times the integral of u prime over u dx. So this is 1/3 times the natural log of the absolute value of u plus c. According to my rule, notice I've got u prime over u. And, lost my pen somehow. I'm going to fill in what u is, which is just 3x minus 1. And you can bring the 1/3 in. If it's a fraction, just leave it out front. Multiplying by 1/3 is easier than taking the cube root. So that would be my answer there. This is going to work very similarly. My u is going to be x cubed minus 2. So my u prime would be 3x squared. Now remember, when you're doing the chain rule, you have to already have the variables or the x's there in place in order to make this work. So we do have the x squared, we just don't have the constant. So if I multiply by a 3 here and a 1/3 on the outside, notice that they would cancel each other out. So this is 1/3 times the integral of u prime over u dx, or 1/3 times the natural log of the absolute value of u plus c. And the absolute value of u is the absolute value of x cubed minus 2 plus c. So that would be my answer there. Now in this one, it might be a little bit hard to see at first that you do have a u prime over u. So if we let u be equal to x cubed plus x, then u prime would be 3x squared plus 1, which just so happens to be what we have in the numerator of this fraction. So this is going to be the integral of u prime over u with respect to x, which is the natural log of the absolute value of u plus c. We didn't even need any constants here. It was really all there for us, which is the natural log of the absolute value of x cubed plus x, all plus c. And that is our answer. Throwing some trig functions in here, if we let u be the denominator, which is tangent of x, u prime is going to be the secant squared of x, which again conveniently happens to be what we have here. So this is the integral of u prime over u with respect to x, or the natural log of the absolute value of u plus c, which in this case is the natural log of the absolute value of tangent of x plus c. And that would be my answer. We can do definite integrals with these just like any other type of function, as long as you can plug the number in to the natural log at the end. So in this case, I would bring the 2 out front. So I would make this 2 times the integral from 3 to 5 of 1 over x dx. And then I would have 2 times the natural log of the absolute value of x from x equals 3 to x equals 5. And I might go ahead and make this the natural log of x squared, because why not? Just makes one less step at the end. So then this would give me the natural log of 5 squared minus the natural log of 3 squared. 5 squared is 25, and 3 squared is 9. And then whenever you're asked to put something in an exact form and you're using natural logs, you do want to go ahead and condense it once you get down to numbers. So I would condense that to be the quotient 25 over 9. And guys, this is where I would leave my answer. This is an exact answer. The natural log of 25 over 9 is a numerical value. It's not a pretty number. It's going to have a lot of decimal places after it, but it is a value and it's a perfectly valid answer. You can also do area of bounded regions, just like you would any other type of function, as long as it is a positive function. And because we have the 2x plus 2 over x plus 1 squared, then you just do kind of want to verify 2x plus 2 over x plus 1 squared is greater than 0 for all x between 0 and 2. So my area here is going to be the integral from 0 to 2 of 2x plus 2 over x plus 1 squared with respect to x. So u here is going to be x plus 1 squared, which means u prime would be 2 times x plus 1 to the first power times 1, or conveniently 2x plus 2. So this will be the natural log of the absolute value of u, because this is the integral from x equals 0 to x equals 2 of u prime over u dx. And that's going to be from x equals 0 to x equals 2. And again, you can go ahead and change your bounds if you want to, or you can just plug in your u, which is x plus 1 squared. So this will be the natural log of the absolute, and this is, squared, so you don't even really need the absolute value anymore. This will be 2 plus 1 squared minus the natural log of 0 plus 1 squared, which is the natural log of 3 squared is 9 minus the natural log of 1, and that is just the natural log of 9 because the natural log of 1 is 0.